Hello, dear students. In the last class, we have to discuss about the addition modulo groups, and previously we have to discuss most of the parts for a group. Examples we provide is a infinite dimensional. We have to take a elements, and this is not a finite. So now let us we have to today's lectures we have to discuss about the finite groups, Cayley tables, how to represent elements of a group is in a Cayley tables, and also the order of a groups. So first we beginning the what is a finite group. So a group G is said to be a finite group if it has finite number of elements, and the number of elements in G is called the order of G, and it is denoted by either this notations or this notations we have to. So simply say that number of elements in a set G is form a under binary operation form a group. So number of element is called is a order of this group, and the group is called is a finite group is there. So let's if a group G has infinitely many elements, then G is called as an infinite group, and the order of a G is infinite. Is a trivial example of a set of integers, set of real number, and set of complex number under a binary operation addition. They form all form as a group, and they are the examples of a infinite groups is there. So most of the examples that we have seen so far are infinite group. In particular, the order of a Z is infinite. Now, for example, we take a if G is equal to Z9, and now you know that the Z9 is the elements of a Z9 is equal to, you have a equivalence class of a 0, equivalence class of a 1, equivalence class of a 2, 3, and so on up to equivalence class of a 8. So we can say that simply is this equal to this, that is a total is number is a number of element, and this is equal to total is a 9. So this means the size of a G we can say is clearly is a order of a G is equal to 9, and if this group of order 9, so therefore we can say that as a finite number of element in the set of a group, so group is called is a finite. So Z9, this is a finite group example of a finite group where the elements are 9, the size order of this group is equal to 9 is there. We take a general is a Zn under addition modulo n, and that is a finite group of order n. You know that the Zn is the equivalence classes of 0 to n minus 1. We know that this Zn, the element of a Zn is simply is equal to, we have a 0 and so on up the equivalent class of a n minus 1. So you see this is n numbers are there. So total numbers are n is there. So we can say that this is size of this order of this Zn is equal to n. So total number of elements is this. So this again is a finite groups of order n is there. Last class we have to define is a un is a all elements of a group value equivalence class of x, where x is the element of a z star non-zero z star n, where non-zero equivalence classes of all this thing. 9 of order phi n means we have to show the Euler function. We have to define the Euler function, and property of a Euler function is later on in this case. So simply we can say that, for example, we take this U9 is the element which are relatively prime to n, that's are 1 is and relatively prime to n. So this U9, the elements are which are element are relatively prime to 9. 1 is relatively prime 9, 2 is relatively prime 9, 4 is also is a relatively prime, 5, 7, 8 are relatively prime. So these are the only number up to 1 to 9 which are relatively prime to 9. So they are the member of this set, and that is the total number of this is clearly is equal to 6. So we can say that the size of this is equal to 6. So phi n is equal, phi 9 is equal to 6. So we can say that this U9 is element of this is another example of the finite group is there. For another, we have to simple example. We say that S1 is clearly this is a group, is only under multiplication is a identity element. 1 minus 1 is again is a form of group because we take any two elements of for example, this if you have a g is equal to simply set is equal to 1 and minus 1. In this case, under multiplication, we have to take operation is multiplication. So identity element is clearly is equal to 1, and every element is inverse of a 1. So we give minus 1 into minus 1 is giving you identity is equal to minus 1 into minus 1. So minus 1 is a self inverse and 1 is also the self inverse. So every element has an inverse, and if you take a product of these two satisfy the close properties. Also closeness is a close and associative, and or commutative is there. So this is a clearly the form an abelian group. And now another example, we have this 4 element. So this is the size of this G is equal to we have a 2, and in this another we have to take a G is equal to we take a 1 minus 1 I minus I. This is again is a form a group, and you can see clearly the identity element in this case also we have a 1, and 1 and minus 1 is the self inverse, and inverse of a I is equal to minus I, and inverse of minus I is equal to I. Then I and minus I are the inverse of each other. 1 is the inverse of itself and minus 1 is the inverse of itself. So this is satisfy all the properties of a group, and these are the under complex abelian group of a complex numbers under the multiplication is there. So here 1 is the identity element for all the cases under multiplications, and we say that minus 1 is a self inverse, and I and minus I are the inverse of each other. Now for a small group under the binary operation, we can completely describe the group operations by drawing a table, and that table is called is a group table or is given by the Cayley. So we can say the Cayley table. This has row and columns. The entry in a row G and a column H, we have to take a this G binary operation of this H. Let's just say that, for example, if we take the previous one, we have to take a 1 minus 1 I minus y, and this is are the subset of a complex number, and binary operation we have to using as a multiplications of complex numbers of this set V. Then this V under this by multiplication of binary operation is a form a group. I just previously show that. Now how we represent this group as a table form, or we can say that is a Cayley table. This is means we have to just say that this is the first row, we have to write the here this is an element, we have to write the binary operation. This is the we have a binary operation. What is the binary operation we have to using, and that is the elements of this set, and this first column and first row represent at the column element of this set. And then just say that if G this previously we just see that we can say the entry of a row is G and a column is H and represented into this. So we have entries of a row is equal to this is G and this is you have a H. So we can say that this is 1 under multiplication of a 1 is equal to 1. So that is why it is 1. And then we have a 1 a multiplication of a minus 1, we getting the minus 1, that is we have to writing as minus 1. And then we again 1 into I is equal to I, 1 into minus I is equal to minus I is there. Similarly, we have to go to the G is this minus 1 into 1, and then we have to minus 1 into minus 1 is equal to 1, and then we have to say that clearly we said that in the form of a this minus 1 into I is equal to this minus I, minus 1 into minus I is equal to I, and similarly all other elements are there. Now you see very interestingly thing by this table we can see because the under multiplication is identity element is equal to 1. If identity element of a 1, you can see clearly this body of in this one, each row and each column exactly one identity element is presenting in there. So we have to just say that into form of this. We have identity element here. This each row and each column, you can see by the row wise and the column wise, we have to string the exactly one element, identity element is present is uniquely in each row, in each column. And now very interestingly, you say that the example I show that previously, say one is the identity element and one is the self inverse, and minus 1 is also is a self inverse. Now you see from here we can see this thing, and this go to the column wise, and this is minus 1 is this is 1 is the identity element again. This means 1 into 1, so is giving the identity element. This means clearly we say that 1 is the inverse of a 1, and from the second one row is minus 1 into minus 1 is again giving the identity element. So we can say that minus 1 is again is a self inverse. Now you see this third we get I, and then we have to getting the minus I, and that is equal to the identity element. Then we can say that I composition minus I is giving you identity element. So the inverse of a I is equal to minus I, and similarly minus I composition with I is giving you a identity element. So in this case, by this table we can represent all the conditions of the group is satisfied. Identity element present each row and each column uniquely, and when identity element is giving, we have the composition of a G and H. G is we have the row wise, H is column wise when intersection is there. So we can say that simply these are the inverse of each element is there. And also you can easily verify the commutativity condition is there. I into minus 1 is equal to minus I, and minus 1 into I is equal to again minus I. So this complete table can be represented as a all the elements are this satisfy all the conditions of a this group. So we can easily by this table we can write all the satisfy all the condition identity elements, every element inverse we can find. So this is clearly I 1 minus 1 I minus I is a form a group under multiplications of a complex, and this size of this group is clearly this number of elements are 4 is a finite group, and the elements are the 4. So order of this group is equal to 4. So when we working because we have to working most of the times of addition modulo and the equivalence classes of this. So I just write most of the time is this is bracket A and A bracket A under addition suffixes and addition modulo B constantly. Therefore we typically use simply A or A plus underscore and B instead of a long as a context of a remain clear. So whenever we will include the equivalence classes brackets when necessary for add clarity. So as an example, I just write the addition table of a Z5 under addition modulo 5. So first we write Z5. I am not writing the equivalence classes. This is 0, 1, 2, 3 and 4, and then you have to just state a total number of this. So Z5 is equal to, you have a order of this group is equal to 5. So now we have to show that this group under addition modulo 5 is clearly is a abelian group under the addition modulo 5. So we have to representing this group by the table. By table I can just explain you by this. So this is a table. I just said that you can just say easily this is addition modulo 5. So 0 plus 0 is equal to 0, then 0 plus 4 is equal to 0. This is the elements row, and this is the column wise we have to element into this form. And if you take, say this is 1 plus 4 is equal to, we have to taking 1 under addition modulo 5, 4 is equal to 5 and divided by 5, remainder is equal to 0, that's why is equal to 0 is here. And again we have to take a 2 plus 2 plus 4, then we have to take a 2 under addition modulo 5, 4 is equal to 6, then we have to divide, this is equal to 1, the remainder is equal to 1, this is equal to this. Now 3 plus 4, we have to take a 3 under modulation 4 is equal to 7. When divided by 5, then remainder is equal to, we have a 2 is there. So similarly, this all the table we have to completing in there, and in this case you can see the under addition modulo 5 identity element here is equal to 0. So we see in this 0 in each and every row and column. You can, by the column wise, this is only 1 0 is appearing is there, and there is again in this columns and this row we have to go into this form. You can see clearly into this form. So each and every row and column uniquely 0 is presenting there. That means we can say that the identity elements is here. And if we see 1 with the composition of a 2 is giving is equal to 3, then 2 is composition with 1, we take again 3. So this satisfies the commutative condition is there. If we have a and B are the element of a Z5, then we can say that A plus under modulo B5 is equal to B under addition modulo 5 A. So commutativity, associativity is a trivial for finite set. We can just say finding into this form, and also we can check the inverse of these elements. For example, you just take a we take a we can take into this form inverse is there. We have to 0 is itself inverse, and then we have a 1 of inverse is equal to 4. Then you have a 1 under addition modulo 5. 4 is giving you a 0. So 1 and 5. So inverse of a 1 is equal to, we have a 4, and 4 is the inverse of a 1. Again, you can just see this identity element is there. Now if we take a 2 under modulo 5 is equal to 3 is equal to is 0. So that means 2 is the inverse of a 3 and 3 is inverse of a 2. And again you check is a this is 2 is a inverse of a 3 and 3 is the inverse of a 2. So we show that each and every element has an inverse, and also identity element is presenting it there. So this is form a group under the addition modulo 5, and that represented by the table. So this is the I represent as a Cayley table for the Z5 to 5 is there. Okay, so now we can say in analyzing this previous table, we notice that each element of a group appear exactly once in each row and its column. So this observation holds as a general property of a group. If G under the binary operation is a group, then for any X belongs to the G, every element Y of a G appears once and only once in a row corresponding to X, especially in the cell where the row X and the column Y intersect. Similarly, a similar assertion hold for columns. This property underscores the fundamental symmetry and structure inherent in groups, reflecting their orderly arrangement and consistent behavior under the group operations. So now I have to give to the another Cayley table, multiplicative table for a U10, and then you know that we take elements of a U10. So those elements which are relatively prime to 10 is equal to 1, 3, 7 and 9. So size of a U10 is equal to, you have a 4. So order of this group is equal to clearly is a 4, and this is a abelian group under the multiplication. So we take under multiplication of a modulo 10, and then you just check. We have to check this 1 intersecting into this 1 as this is. So and another 3 and 1, you have to the 7 and you have a 3 and 9 into 1 is there. So U10 you can just see this 1 is itself inverse. We have a 1 into under multiplication 10 is equal to, you have a 1, and now you see the 7 and 3, 7, 3 under multiplication modulo 10, 7 is equal to, you have a 21, and then you have a remainder is equal to 1, and similarly 9 under multiplication modulo 10, 9 is equal to, you have a 1. So inverse of a 9 is itself, 1 inverse is itself, and 3 and 7 are the inverse of each other. So we can simply say that each of element of this identity element is uniquely present is there in the table. Each and every element of the set is uniquely, each row and each column you can find this. So clearly we say that this satisfies all the properties of 5 the properties of a group. So this form an abelian group under the multiplication of modulo 10 is there. Now I just go to the next examples. That is a very interesting and very famous group. We have to know that is a quaternion groups. That is a number of elements are 8. Previously we have to, all the groups we have to discussing now is a finite groups, they are abelian. Now this is the group which is not a abelian group. Why? Because we have to take elements are this. So this is total number of this size of a G is equal to, you have a 8. So this is a, that's why it's called is a quaternion group. So and this elements are plus minus I, plus minus j, plus minus k, I, and you can now the multiplication identity here is equal to 1. 1 is the identity element is clearly presenting here. So is this condition is you have to just check the I square and j square and k square is the property is equal to minus 1, I j is equal to minus ji is equal to k, ji is equal to this, all this form we have to into this form. So we just we have to just say that ij is equal to minus ji is equal to k, jk is equal to minus kj is equal to I, and ki is equal to minus ik is equal to j is there. Now you say that this I or j is not the same k, so this ij are different, so we can simply say that this is a non-abelian group is there. So this group is not abelian. Again we have to the j and k is not the same, j k is the kj and ki I, and this is also is not the same is there. So clearly we can say that this is the non-abelian group. Now we have to check other properties of a group is satisfies or not. We have to representing this again by the Cayley tables. So Cayley table is saying that we have to write under multiplications the first row of these elements is the elements of the groups 1 minus 1 I minus I, j minus j, k minus k, and this is first column is also same elements of the groups elements are there. Then we have to take a composition of this under multiplication 1 into 1 1, 1 into minus 1, this is giving the same. Now we have to just check the I into 1 is equal to I minus y is equal to I square is equal to, we have to just previously show that minus 1, I and minus I is equal to 1, and then similarly I into j is equal to k, I into minus j minus k, I is to k minus j, I into minus k is equal to j are there. So this we complete this elements of this table, and now you see the elements of this table, all the elements are uniquely representing each row and each column are uniquely representing the elements of this column. Each row we have to find the elements of this set, each column is also find the elements of the G is there, and each row and each column one is presenting is there. So we can simply say that so we can simply say that we can simply say that this is 1 1 1 1, and we have a 1 here and here and here. Now we just see that the 1 is the inverse of itself, the 1 into 1 is equal to then minus 1 also is the inverse of itself, and now I is the inverse of a minus I, and minus I is the inverse of a I, and j is the inverse of a minus j, and minus j is the inverse of a j, k is the inverse of a minus k, and minus k is inverse of a k. So we can see that means every elements we have to find has an inverse is presenting there, identity elements are there. So this satisfy all the properties of a group, and that is a group is clearly this is a non-abelian group. We can from here is also I into I into j is equal to k, but j we just say that I into you just said I, and we have to take I into j is equal to we have to getting the k, and then we have to take a j into I is equal to minus k. So we simply say that I into j is not equal to j into I, so it's not a commutative condition. Similarly, we can say that I into k is not equal to k into I, and j into k is not equal to k into j is there. So this quaternion group is a group, but and this is clearly is not an abelian group is there. Now I just interesting very another example for a finite group of a has a element 4 elements, and binary operation we have to define is there. If take a square of elements is giving the identity, if we take a composition of a composition B and B composition C is giving the third element, and B composition C and C composition B is giving the A, and C composition A composition C, what is the remaining element third is equal to B is there. So binary operations we define in such a way whenever square of elements is equal to identity, and we take a if the composition of AB is produced is a C, and we have a B of A as again C, a B or C is giving the A, and C of B is again A, and similarly C of A is equal to B, and A of C is also is equal to B is there. So now we have to representing this elements into a this group tables and then Cayley tables, and then we have to try this. So this K4 forms an abelian group with the identity element we have to taking E, which is known as a Klein-4 group, and this Klein-4 groups is the name honors to Flex Klein. The Klein is a small in the word is a German words, you have to know that. So this group is called is a 4 group also. That is because in the K4 there is an element of this we have to say that simply is equal to K4, the size of this is equal to 4. So E, A, B, C is a standard elements of this types, and this satisfy this condition is also called is a K4 group or the Klein-4 group is there. We have to representing this form by the table of this. You can see is again E, A, B, C, and then E composition E is again you have a simply is equal to E is there. Now A composition A we have to define is E. So A square is equal to identity, B square is equal to identity, C square is identity. That means this is the group is a special type where whenever we have each element has its own inverse. A composition A is identity, then inverse of A is equal to A. B composition B is equal to identity, then the inverse of a B is again itself. C composition C is equal to identity, then the inverse of a C is also the same element. So we can say this all the elements of a as a self inverse. So this is the clearly is a finite form a group. One group we have to say into this form this so we have to write as for example we have a you have a we have to just write sorry this group I am interested into this U10. So we take a U10, and now this sorry we have to take this U10 sorry we have to take U10, the element is equal to 1, 3, 7 and 9. So these are the 4 elements are there. Now you see the previous groups, you see this this is the property is satisfying this satisfy. Now here is also you have to just set 1 into 1 is equal to 1. We have a 3 into 3 sorry, this is we take a sorry, this is no. Okay, this 1 3 7 9 is there. Now see, if we take some elements like this, 3 into 3 is equal to modulo 10 is equal to 9, giving so inverse of a and then you have a 7 into modulo 10, 7 is equal to again 49, you have a 9, and then you have a 9 into 9 modulo 10 is equal to you have a 1. So if we just check in the table of this, we just check into here, we have to just take the 1 is the inverse of a 1, 3 is the inverse of a 7, 9 is itself inverse, so 3 and 7 are the inverse itself is there. For examples, I just take suppose we have to take a U7. U7 is the which is the element of a 1, we have a 2, 3, and then we have a 4, and then we have a 5, and the 6 is are there. Now we check is this is a form a group under the multiplication modulo 7 or not. The multiplication modulo 7, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So 1 into 1, 1. So we have to just say that into this form we write. Okay, so now okay, 1 into 1, so 1 into 2, 2, then 3 and 4 and 5, 6, 2, 3, 4, 5, 6, and this is under 2 into 2 is equal to 4, 2 into 3 is equal to 6, 2 into 4 is equal to 8 is equal to 1, 2 into 5 is equal to 10 is equal to 3, 2 into 6 is equal to 12 is equal to 5. So now you see the elements of this table is 1, all the elements are the members of this set, and this row is also the member of this set. 3 2s are 6, then we have a 3 3s are 9, and then we have a 2, 3 3s 4s are 12, we have a 5, and then 15 we have is equal to 1, we have a 18, so we have is equal to 4. So all the elements of this table are in this form is there, so we can just check all other elements of this also the satisfy. Similarly, we have to continue this form, and then you see we have clearly see that these are the elements, all the elements of this tables are the members of this group are there. Each and every row is presenting identity elements are there. We have to just say that similarly, or this we have to finding into all these things is equal to satisfy to complete this table. So this U7 is also form a group under the multiplication of this, and then you have to just say that U7 order of a U7 is equal to we have a 6. So under multiplication this also form a group is a form a group under the multiplication table by the Cayley table. So in this lecture we have to see how to a finite number of groups we can be easily construct a Cayley table, and then solve identify the groups, what is the identity elements and the inverse of these elements. So I have to stop this lectures here, and in the next lecture we go to the properties of a group we have to discuss, because we have to say that the identity elements in the table I just said that every row and every column as a only once time is the identity is present, and the corresponding the inverse when you're talking the inverse of this, then the each element has a unique inverse is there. So in the next class we have to continue for the properties of a group, different type of property we have to discuss into next class. Okay, thank you for this. We have to continue into next lecture.